Imagine a computer that doesn't just calculate, but thinks like a brain. A system that learns, forgets, adapts, and reacts, all while consuming only a fraction of today's power. Welcome to neuromorphic computing, where physics meets biology to build machines that think in hardware. Traditional computers follow the von Neumann architecture, where memory and logic are separated. This constant data transfer creates the von Neumann bottleneck, wasting energy and slowing performance. The human brain, however, performs computation and storage in the same place, inside neurons and synapses, achieving unmatched efficiency. Neuromorphic systems mimic this biological approach. They use memristive devices, which combine memory and processing in a single nanoscale unit. A memristor remembers how much current has flowed through it, just like a synapse strengthens or weakens with experience. Now enters the real breakthrough: low-dimensional materials, substances only a few atoms thick that operate on quantum principles. These are classified by dimension. Zero-dimensional materials, like quantum dots, confine electrons in all directions, giving discrete energy states. One-dimensional materials such as nanowires allow electrons to flow freely along a single axis. Two-dimensional materials like graphene or MoS form atomically thin sheets that can be stacked into van der Waals heterostructures, unlocking exotic electrical behaviors. These materials give engineers atomic-level control over neuromorphic behavior. Their defects, interfaces, and topology determine how synapses behave, allowing us to tune memory, speed, and plasticity directly through geometry and chemistry. The result is multifunctional, MF, neuromorphic devices, hardware that can sense, learn, and compute simultaneously. Imagine a single device that detects light or pressure and instantly adjusts its internal state to remember that input. This is adaptive intelligence written directly into matter. A key concept here is the spiking neural network, SNN, a model inspired by how biological neurons communicate through discrete spikes of voltage. Instead of constant signal flow, these spikes occur only when needed, slashing energy use. Low-dimensional memristors naturally produce such spiking behavior due to their nonlinear switching properties. Networks built from these devices can perform pattern recognition, decision-making, and learning in real time with minimal power. They are ideal for edge AI, the Internet of Things, and autonomous robotics, systems that must think locally and fast. Take wearable robotics. Prosthetics, or exoskeletons, could use low-dimensional neuromorphic networks to interpret muscle signals, adapt to movement, and feel through sensors integrated into the hardware. These materials allow machines to process sensory data and respond on the fly, blurring the line between biological and artificial intelligence. Of course, challenges remain. Controlling device variability, scaling up arrays, and ensuring stability over time are major hurdles. For instance, in two-dimensional memristors, switching ratios don't always scale predictably due to competing atomic mechanisms. Mastering these effects is key to consistent performance. Progress also requires fusing materials science with algorithm design. Neuromorphic algorithms must align with the physics of these materials, using their inherent quantum dynamics as computational features, rather than treating them as noise. Despite the obstacles, the promise is enormous. Low-dimensional MF neuromorphic systems could deliver computation that's parallel, fault-tolerant, and self-learning. Qualities the brain evolved naturally. They could power autonomous agents, smart sensors, and cognitive robots capable of perception and adaptation. The field is now shifting from discovery to design. Researchers are standardizing ways to test, model, and simulate these nanoscale systems. Each step brings us closer to quantum neuromorphic intelligence, machines that merge computation, memory, and sensation into one unified physical process. Low-dimensional materials are giving rise to hardware that doesn't just run code, it learns from experience. This is more than engineering. It's the dawn of machines that compute like living systems. The future of AI may not be coded. It may be grown from the quantum fabric of matter itself.